Hey guys, this is JP Monk from Planning Seeds Tutoring. In this video, we will be discussing the four fundamental forces of nature and how they come together to make the universe we live in. Don't forget to use my referral code JPMonk20 to get 10% off on your next tutoring package. We generally define a force to be either a push or a pull. However, there are four basic forces, also known as the fundamental forces, which determine how objects and particles interact with one another and how certain particles decay. These are the gravitational force, the electromagnetic force, the strong force, and the weak force. These four fundamental forces account for all natural forces. So let's go ahead and start off with gravity. This tends to be the most misunderstood force of all time. Yes. It was originally described by Isaac Newton in the 1600s, and he gave a notion that gravity acts between objects that have a mass. He came to the conclusion that the force of gravity is proportional to the mass of an object times the mass of the second object divided by the distance between them. So as you can see right here, we have, let's say, an object here, the blue object, and an object here, the yellow object, let's say the Earth and the Sun. In that case, the force of gravity between them is proportional to the mass of the Earth times the mass of the Sun divided by the radius squared, the distance between them squared. As you can see, I did draw it from the center of the objects to show that it's from the center of their masses. A little bit later on, we got Henry Cavendish to get a very, very close measurement for the proportionality constant. He measured it to be about 6.74 times 10 to the negative 11. It's actually 6.67 times 10 to the negative 11. Just a very small, minor difference. So this gravity constant 6.67 times 10 to the negative 11 Newton meter squares per kilogram squared is going to be what gets us our new force of gravity to be the force of gravity is equal to G, the big G, times m1 times m2 divided by r squared. However, in the matter of a few centuries, Albert Einstein came to the realization that this understanding of gravity breaks down when we talk about objects that are moving at near light speed, and when we're talking about objects that are so small that they belong in the quantum realm. So he came up with his own idea, the theory of general relativity, or the idea that space and time are both mended together as one fabric of space-time, and the masses are just curves within a fabric. It's kind of like placing bowling balls on a trampoline. You would notice that when you place those balls, there are actually like dents within them, and if you place like another object there is near it, there's going to be that dent has like an effect on it. That's what gravity itself is. However, as you can see, this equation right here is not the prettiest equation in the world. And what it actually says is that the curvature of space-time, the curvature from all the stuff in space-time, plus the curvature of space-time itself. So this right here is the curvature that's caused by everything that's inside of space-time, like everything as in like all the objects that we're talking about, plus the curvature of space-time itself is going to get us the mass energy kind of relation itself, the pressure, the effect on the mass energy. A little bit very difficult stuff to understand right now. Anyway, let's go on. And the thing about gravity though is, from what we know, it has infinite range. This r squared could be a value that's very, very high. All that would mean though is the force of gravity at that distance is going to be very, very small. However, it's still going to be a non-zero value, and so it's going to exist. Force of gravity is always an attractive force, and it's going to be effective at all ranges, at all distances. However, it is also the weakest force by a significant margin in comparison to all the other fundamental forces. Now, we have a theory, we have not yet theorized based off of quantum mechanics that there is a possibility of the existence of gravitons, which are supposed to be the force carriers for gravity, for the force of gravity. However, it has not yet been found yet. We hope to find it, but it's very, very hard to find it because based off mathematics and stuff, the requirements to find a graviton may mean that we are trying to look for something that's smaller than a Planck length, which is the smallest length, the unit of length that's supposed to be possible. So we are challenging the impossible by trying to find a graviton. Next, we have the electromagnetic or the EM force, electromagnetic force. And the electromagnetic force can be given, the equation, the best equation to represent it would be the Lorentz force. The Lorentz force, which gives the idea that the force, the electric force itself, the electromagnetic force is given by both Coulomb's law, kq1 times q2 over r squared, or in other words, q times the electric field, which is the same thing as Coulomb's law, plus q times the velocity of that charge crossed with the magnetic field that it goes through. As in the perpendicular, cross just means that it's just being multiplied by a perpendicular magnetic field. Anyway, so this equation itself kind of gives you the idea behind an electromagnetic force. The electromagnetic force, though, is probably the most important force for us as a human or as any kind of being. It's the force that holds all molecules together, and it ensures that electrons get pulled towards the nucleus. However, they don't get into the nucleus because of their extremely high speeds, extremely high velocities that go in a circular motion, so that centripetal force kind of exists. Now, the electromagnetic force is also pretty much every interaction that you can probably think of, except for us getting pulled down to the earth. Every other thing that we talk about usually is something to do with electromagnetics. Just typing or doing any kind of physical motion and stuff, that's all really based off electromagnetism. Light comes as a result of electromagnetism. There's light, visible light, infrared radiation, radio waves, they're all just forms of electromagnetic radiation. Photons are the force carriers of the electromagnetic waves. Once again, electromagnetic waves, electromagnetic forces, just like the gravitational force, is also of infinite range. As you can see right here, the kq1, q2 over r squared. This means that r is an infinite range. It can go as far as you need it to go. So at any distance, there's still going to be some electric force. Even if this value right here, even if there is no magnetic field, you can still get an electric field. Even if there is no electric field, you can still get a magnetic field. And using that, we can figure out how much the electromagnetic force itself is. Next, let's talk about the strong force. So what the strong force is, based off the electromagnetic force, we should not be seeing neutrons clumped together, or not neutrons, protons clumped together inside of the nucleus. They're very, very close to one another, and they have positive charges, which means that they're like charges. They should not be together. They would be repelling each other all the time. And the electromagnetic force between them is very, very high. However, we have a force known as the strong force, which is even stronger and pulls them together. However, what stops atoms from being just like huge clumps of just protons or neutrons and stuff is the fact that the strong force has a limitation. It has a very, very small radius that it can cover. And if you go past that radius, it's not going to work. It's kind of like a Velcro. If you don't have the attachment to the Velcro, the other side of the Velcro itself, it's not going to stick to anything. It's like trying to stick two things that are not touching each other. Now, the strong force not only has the interaction between the protons, neutrons, and the protons themselves, they also have the interactions. It's also in charge of the interaction between the subatomic particles, which make up the protons and stuff. So we have three quarks, which make up a proton, and three quarks, which make up a neutron. We have two down quarks for a neutron and two up quarks for a proton. So their charges are going to be 2 plus 2/3 plus 2/3 minus 1/3 minus 1/3 minus 1/3 plus 2/3, which just adds up to being 0 charge here for neutrons and plus 1 charges for the protons. And the gluon is the force carrier of the strong force and is in charge of physically pretty much gluing these together. Finally, we're talking about the weak force. The weak force is less of a force than it is an actual interaction. So the weak force is in charge of most radioactivity and things that we were talking about, things like nuclear fusion and stuff. It's all actually run on the weak force. So unlike the other forces, the weak force is in charge of making decay, making an object decay. It has the important role. It's important in that it determines whether or not like a star is capable of powering itself, and it determines whether or not certain elements are even possible to be created and stuff. Well, what happens here is there are two different methods of decay that we commonly look for. With the weak force, it's beta plus, and we also have beta minus. So in beta plus, what we tend to see is we see two protons which come together to create a proton and a neutron. And with this combining together, we're going to get, instead of just holding onto that same amount of protons and neutrons, we would be getting a new neutron, but we just converted a proton into a neutron itself. So this is what we call the beta plus decay. There's also, so the byproducts here are a neutrino, this orange portion right here, that's a neutrino, and the positron. A positron is just a positively charged electron. It's an an example of antimatter. Antimatter being any kind of matter-based objects, matter-based particles to be having the exact opposite charge. In beta minus decay though, we start off with a proton and a neutron. We give away, instead of a neutrino, we give away a antineutrino, and instead of giving away a positron, we give away a electron, and then we get two protons. And that's what we call the beta minus decay. So the strong force and the weak force actually work at very, very small distances. The weak force being an even smaller distance than the strong force. And the weak force is dependent on W plus or minus bosons, as well as Z bosons, phenon bosons. Now the weak force is very, very weak, but it's nowhere near as weak as the force of gravity. The only reason as to why we inherently feel the force of gravity very commonly is because of the size of the Earth itself. The Earth has a huge size, which makes humans or any kind of normal beast seem very, very tiny in comparison. So the force of gravity is just stupendous to overcome. On the other hand, electromagnetic charges, you tend to see very, very small charges in the microcoulombs and stuff. The strong force is what pulls up atoms together. This is the strongest force, and the electromagnetic force comes in after that. It's about 100 times weaker than the strong force, and the weak force about a couple 10,000 times weaker than the electromagnetic force. All right. I appreciate you guys for taking your time to watch this, and I hope you guys come back for a later episode or video. Thank you.